Also true. Okay. Hey guys. Hey, so let's get started with our session on Hadoop and Java, right? Before we get started, quick show of hands. How many of us here have used Hadoop before? You have? Okay. How many of us? Yeah, I mean, whether it be a hobby or as part of your job. That's fair enough. You have? Okay. All right. So, how many of you have heard of Hadoop? Hadoop, big data. Okay.
Heard and wanted to use.
Okay.
But didn't I someone to get started, to help to get started? Yeah.
You've not got a chance yet.
Yes.
Okay. It's an interesting technology with a lot of applications, right? Today, let's see if we can cover two things about Hadoop. One is to get some understanding of what Hadoop is, what are the components that make up Hadoop, right? And two, we'll try our hands at writing a program that runs on Hadoop, right? The goal being, we are going to look at a video that went viral, right? In 2006, it was called the Star Wars Kid, right? That video had about 900 million hits. And fortunately, one of the guys who owns a website through which this traffic was routed, he published his Apache logs, right? So we can do some mining on those logs to kind of try to understand how that event went on, yeah? All right.
Will you cover the entire Hadoop ecosystem?
No, not really, right? So I think what we want to do here is to try to get an understanding of how Hadoop works, right? And Pig and Hive are layers on top of that, right? So they are kind of like abstractions over Hadoop, right? And they are pretty easy to get once you understand how the underlying system works, right? Hive is basically SQL, so that's easy enough. And Pig is also similar to Informatica, it's like an ETL language, yeah? Alright, so this about me. I am a Java developer. I am also a solution architect. Currently, I work with PayPal, which is an eBay company, right? Alright, we spoke about this a little bit just now. Two goals for today. One, we want to understand how Hadoop works internally. Fundamentals, not a lot of detailed stuff, but at least we want to understand what are the different pieces, how they work together, and how we as programmers need to use those things, right? And goal two is we'll write a simple MapReduce program on Hadoop. We'll be using Pig, right? We'll not be working with direct MapReduce classes, but we'll write a program to parse this Apache server logs for the viral video that we just spoke about, yeah? Hey, and a lot of this material that you're going to see today, the slides are from Cloudera and Stanford, right? I have adapted from that. Okay, so some context. So before big data, we've had databases, right, for decades now, and they've been doing a good job, especially relational databases, Oracle, MySQL. So why move from databases into big data, right? Why this sudden transition? It's not really sudden, but why this transition? Why do you need it? So if you think about it, databases, they are structured data stores in the sense that you define columns, then your data is in the form of rows, and each row has those set of columns, right? They are structured, they have a form to it, and for certain operations they are really good, right? They come optimized for certain operations, for example, adding, inserting rows, updating data values that are already present in the database. These are things that databases excel in, yes? They also have a lot of additional facilities that they provide, for example, indexing, right? If you put a lot of data into your database, you want to be able to get at it very quickly. So all the databases come with some form of indexing, B-tree, B+, hash, whatever it is. Ultimately, they manage those indexes for you. All you have to do is define the structure, give the data, and it will build the index and get the data for you quickly, right? So given that they do come with some advantages, why are we looking at big data? And this one, right, enforcing data quality is a big plus. Relational databases, your referential integrity, primary key, unique constraints, right? These are all things that we have all gotten used to. If you start moving to the big data world, these things are not there yet, at least not there in large part, right? So these are things that we lose right out of the gate, right? If you lose, say, something like a primary key constraint, right? If you start having 4 students with the same name in one class, then you're in real trouble, right? The data is all, your sanctity of your data is very important. It doesn't matter if you use Hadoop or Oracle. Yes. Okay, so given that they do come with a lot of advantages, why do we want to move to a big data platform, right? What does that bring that Oracle does not give us? I think it goes down to, I don't know if you can see a mouse here, you cannot? Okay, there it is. So it goes down to more hardware limitations, right? End of the day, relational databases were designed to run on one box, maybe a rack, right? But not on thousands of nodes. And the limitation with that is, an hard disk at the end of the day is still a motor, a disk spinning on a motor, right? So there is a limit on how quickly we can read data off of that disk, right? If you make the motor faster, then your disk is going to burn out quicker. If you make it slower, your data comes out slowly, right? And all the other really quick data stores, whether it be SAN, whatever data technology we want, they are very expensive, right? So there is a total cost of ownership element to it. Yeah. So this is one limitation. If you have 1,000 machines, relational databases were not designed for that kind of architecture, right? And this is something that comes to play. The number is not fixed in the sense that relational database can hold 10 terabytes of data. That's not really true, right? Even today, I work with databases where we get 0.5 terabytes added every day, right? So that number is not fixed, right? But it is a good indicator. Beyond that number, you're going to start seeing problems. You're going to start building custom role solutions to take care of your data. The database itself is not going to come out and help you much, right? So how do you scale past 10 terabytes? When we say scale past 10 terabytes, let's not think of say 20. Let's say 2000 terabytes, right? That's a big number. Not all of us are going to use that kind of data. Not all the problems in the world require that size, that much volume of data, right? But in the sense that what we are trying to consider here is, if your data volume is big, can we use a platform that's naturally designed for that kind of data volume so that your job becomes easier, right? Whether it be 100 terabytes or 500 terabytes. And we will see during our demo and hands-on now that you don't really need even terabytes, right? Even if you're talking gigabytes or megabytes, you can still use this platform. You start here, and as your data starts growing, as your use cases start growing, as our experience starts growing, you can deploy and build more complex use cases on top of this, right? Alright, so this is what we are looking at. As developers, what we want is, if I have a 1000 node cluster, or I have one laptop on which I am coding, I want to write one program that will run on both, right? Essentially, we want an operating system which will take our programs and run it on this big cluster, right? What does Windows or Linux do for us? You give it a jar, right? It takes care of abstracting away the hard work in reading data, whether it's a data disk is on a network, it's attached to your own computer. It abstracts that away from you. It abstracts the complexity of interacting with the CPU and getting your instructions executed, right? You have your JVM, you have your OS. So Hadoop is kind of like that. You can think of it as an operating system for big data programs. So irrespective of whether you have one jar that you want to run on your laptop, like what we will do today, the same jar you can deploy to 1000 machines, and the operating system or Hadoop will take care of running it in an optimal manner, right? Alright, and how does it do this? Some of the basic tenets in enabling our programs to run in this manner, right? We have to follow some rules, right? We simply cannot say, for example, go and access data all across those 1000 nodes and then expect the program to still perform. So there are some basic rules that all of us will follow when you're writing programs that are intended to be deployed on Hadoop, right? And the rules are very simple. One rule is, we won't talk across nodes, right? If there are 1000 computers, there will be 1000 copies of your program running on each of those 1000 computers, and each copy of program will use the data that's on that node. Right? Yeah? Okay. That's called shared nothing, right? Shared nothing. Everything that you need will be on your node. And no communication between nodes. Another thing that's not put here is, you should expect your program to run multiple times, right? Say, for example, you have a data set that's 10 GB, right? We'll assume 10 GB. You have 10 nodes, which means it's probably the best way to do it is have 1 GB per node, copy 1 GB of the 10 GB data set to each of those 10 nodes and run 10 copies of your program, right. One thing that we should be aware is your program might run 10 times, 11 times, 12 times. It really shouldn't matter. Given that 1 GB of data, you should always process it and produce the same output. Yeah? Make sense? Okay. All right. And this is something that we are going to see over and over again. Most of the times Hadoop takes care of this. Making sure that your program runs on the node where the data is, but sometimes we want to design the storage in such a way that in a more optimal manner, right. But this is something that you will start encountering, you will start seeing right away, but you will really need to think about this as you start to deploy more advanced use cases, and that is we want the data to not move, right. Essentially the biggest bottleneck in parsing and processing large data sets is the I/O. Yes, whether you hit the network or hit your hard disk, the computations are relatively cheap. It is the process of getting data from the hard disk to your memory and then reading it and then writing it back, that's really slow, and doing it in a random manner is terribly slow. We are talking orders of magnitude slow, right. So one of the things that we want to do is, your jars are relatively small. At best your jar is going to be say 100 MB including all your dependencies. So let's move the jars over to the nodes and store the if you get a 10 GB file, break it up into equal pieces, put it on all the computers that are available. As soon as you give the jar, and the program inside the jar can keep changing, the data does not change, right. The program that runs on the data changes. Copy the jar to all these nodes and start 100 copies of your or 10 copies of your jar. Yeah, that is all there is to it. Not a lot of complexity there. The reason why we spoke about us needing to expect our jobs to run multiple times is twofold. One is, as the number of nodes in the network in the cluster grows, some computers are bound to fail, right. And this is expected, we design for it, we anticipate it. If you have 1000 computers, or at least 5 or 10% of it will continue to have some problems, right, whether it is your hard disk failing or the network cable having some fault. Some computers will go offline all the time. So if your job is running on one machine and that fails, your job will automatically be restarted on some other machine, right. So in this case, maybe if you had 10 nodes and one went down, your job will run 11 times, right, which is why it is important for us to understand that given an input set A, your output should always be B, irrespective of whether I run it once, twice, thrice or 10 times, right. One of the principles that we need to follow. Okay, so this is what Hadoop brings to the table for us. One is automatic parallelization. It will run your job in the most optimal manner that it can, given the hardware capabilities that are present at the time when the job is going to run, right. Today you have 10 nodes and you run a program, it returns in say X minutes, right. Tomorrow your data grows twice, your cluster size also doubles, the program will still return in the same time, right. And that is something that the operating system is going to guarantee. We as programmers do not have to do anything for it. Yeah. And fault tolerance, again we just spoke about it, some things are going to always go bad and you need to work around that, and all that logic is built into that operating system. Alright, so let us quickly jump into details. We want to understand how to use Hadoop, right. The focus here is not how to administer Hadoop, but really how to use Hadoop. So let us talk about how we are going to program. Yeah. So the programming model in terms of how do you write programs that use data on Hadoop, twofold. One is the map phase, another is the reduce phase, right. Pretty straightforward. All our data is going to be in the form of key value pairs, right. If you are Java programmers, your hash maps, right. Sometimes the key values may not carry a lot of significance. Let us say for example your input, like what we are going to see today is a server log, right. So how do you break a server log into key value pairs? Yeah, it could be you could use the line number 1 value will be your entire line number 2 value will be the entire line, right, and the line number does not carry any significance for us. We are interested only in the data, but the programming model requires the input to be in the form of a key and a value. Make sense? Any questions up till here?
It means it goes into the hash table completely by line number 1 is first is a key 1 and it's the entire line and the 2 entire line
Absolutely. So, when you are using abstractions like pig or hive, when all that they are doing is they are writing the Java program that we would have written under the covers, right. When you run your pig script, we will do that in a minute. We will be writing something similar to a SQL or a kind of like an step-by-step instruction on how to go about creating the result, but we won't really write the Java code, right. The underlying pig framework will then sit down and write a Java class, which basically is something that we should have written, but we were too lazy to write, so it's going to write it for us and then run it on Hadoop. And there, that Java code, when it runs, it will go read the data in Hadoop and it will give your program two things. One will be a key, which will be the not the line number, but the byte offset from the start of the file, right. Basically, if you have two lines, first line is starting at byte 1, right, second line is starting at byte 101, right. Key for the first line will be 1, key for the second line will be 101. It's just a running number so that the key is unique, right, carries no significance for us. If you think about it in terms of reading a database and processing it on Hadoop, your key could be your primary key. In that case, there actually might be some value in that key value pair. If you are reading text files, usually they don't carry value.
Yeah, so in this case, processing the log files in this example, it is assumed that the entire log data is present in all the nodes of the process.
Yes, the log data is split and some parts of it are put in different nodes. So that each node, when your Java code runs on each of those nodes, you can process different pieces of that log, right. At a time you are processing 10 pieces of that log, 10 segments of that log, and then you will combine it.
So all these internal combining fault tolerance is taken care of by the Hadoop system?
By the Hadoop system, yes. Yes, they are taken care of by certain components of the Hadoop system. We will briefly talk about that in just a couple of slides. So, from a programming standpoint, there is a key and a value, right. If it is a text file, the key does not carry a lot of significance for us, value does. That is the entire line you are going to get as a string, and then you can extract whatever data point you want from that line, and again you create a key value, right. You are going to very quickly get good at creating key values, because that is all we can create, right. So, you will read the line and then you will create another key value. If you are reading an Apache log, it might be the instant in time when the line was created, it might be a sequence number. If you are interested in, say, what was the person who referred you, that might be your referral. Whatever data point you are trying to parse in that row, you will create a key value from that row, right, and you will write it to your output. Yes. So, maybe we will take an example of database which will be more straightforward for us, right. Let us assume we are going to parse employee data using Hadoop, right. You have two tables, one is the employee table which has the employee ID and name, right, and next is the employee address table which has the employee ID and address. Yeah, and if you parse this using Hadoop, your first input will be, say, row num will be 1, that will be the input to your map phase, row num 1, and your entire row will come in, say, employee ID 1, name is equal to X, right, and your second table will come in and that will have employee ID equal to 1 and address is equal to, say, Velicheri, right. Make sense?
Yes.
So, when you are going to what is the output from the map phase here? You will probably exclude all the columns from that row. You will just pick, say, whatever columns you are interested in and keep the employee ID as the same, because you already have an unique and interesting employee ID which is the primary key. So, you will emit, or your output will be employee ID and just the fields that you are interested in from that row, right. You are taking an input and mapping that input for data points that you are interested in the subsequent phases, and you will output it from map, right. Stay with me here. Now, it gets interesting, because what the framework is going to do for you here is, once all the maps are run, you have two employee ID outputs in our example, right. One employee ID output will be from the employee table, second employee ID output will be from the address table, right. Now, what the framework is going to do is, it is going to combine all these records by the key. So, what you will get is essentially a key, comma, list of outputs from the other two initial two map tables, right, and this will get fed to what is called a reduce phase. Essentially, what you did is, in the first phase, you mapped the input to some key value pair. In the second phase, you are reducing all the outputs from the map phase and creating one data point, that is your final output, right. So in the reduce phase, what you might do, you will get an input that says employee ID 1 with a array, and the array values will be your name x and x comma Velicheri, right. That will be input to your reduce phase, and you will probably emit the same thing. You will say employee ID output employee ID 1 comma name comma address. You just did a join, right, and that is really how a join will work. Few ways to do join, but this is one way you might implement it, right. Make sense? So a lot of the programming tasks that we can do can be fit into this model, and the advantage is this model is automatically scalable. If you have a public static void main piece, code piece which you want to run on 1000 nodes, it's difficult for us to parallelize it, right, but this model is easily parallelizable. Okay, so that's about MapReduce. This is what we just spoke about. You get some data points from your source data, input data. You categorize that and say all these records belong to this particular key type, and that is what you are outputting, going to output. And then in the reduce phase, whatever keys you gave, they will all come together and come into reduce, and then you will further reduce that and derive some data point. In the reduce, you might be doing a lot of things, right. You could count, you could do average, because you have all the data points for that key in one place. Yeah, does that make sense? Makes sense, right. So this is something that we need to get our heads around. In the reduce phase, in the map phase, everything is going to come into your mapper, and there you are going to pick a key and value to emit, right. In the reduce phase, all the values for that key are combined and sent into your reducer. That is a good place for you to do all the aggregation stuff, right, because all the values for that key are in one place. So average, sum, whichever you want, you can run there. Yeah. Okay, so some of the assumptions. So now we know we can run these programs, but you had asked a question saying how is the data stored, right? So data is an equally important part of the puzzle, because you need to distribute this data. When you say a program goes to the data, then data should already be distributed so that your program can run in n copies, right? So that is another component of Hadoop. MapReduce was the first piece. The second piece is the data storage layer, that's called HDFS, right? Both of these work together, but they can also be used independently. HDFS is basically a reliable data store, redundant data store. What all that means is, if you give it a say 10 GB file, what HDFS does is it breaks it into 10 pieces, right?
Stores in 10 nodes.
Stores in 30 nodes, absolutely. So because we expect these nodes to fail, it will create 3 copies for each of these pieces and store 3 copies, each copy in a different node. So essentially your 10 GB on 10 nodes becomes 30 GB and 30 pieces, yeah, which means essentially even if one node goes down, you still have 2 copies to reconstruct this node, right? And it does all this work in the background, right? One node goes down, it immediately detects that you have only 2 copies left, so there is a thread to that file, so it creates a third copy in some other node. All the work that goes behind in maintaining the reliability of the data, it's going to take care of.
Job tracker will obviously take care of all those things.
Yes, not the job tracker, but actually the name node and other pieces of the HDFS. Yeah. All right, and some of the assumptions, underlying assumptions, you write to the file, you cannot do random updates to the file. That's obviously very slow. You can append, you can insert new data, you can read data sequentially. A lot of limitations, right? If you cannot do random updates to a file, it immediately handicaps a lot of programs that we write, right? You're reading a record, if you cannot even update a single piece in the center of that record, then it's very tough to program in that environment, but apparently not. A lot of real-time databases have been developed on HDFS. HBase still continues to be a good candidate for that, and those databases do allow random updates, right? They just cannot do it on the disk, right? So from our standpoint, you cannot update files. You can add data, you can delete data, you can read data sequentially. When you read it, you get 64 MB at a time, yeah, which are really big blocks, right? Typically we are reading 4K if you are on Linux. You are reading 4 KB at a time, and these guys are saying they are going to read 64 MB at a time. The assumption is all our files are terabytes, right? If our entire file is only 4 MB, then you will get only 1 read. Alright, so we already spoke about a lot of these things. Alright, so let's look at the different pieces, and before we go there, probably quickly look at who is using Hadoop. Lots of pieces, lot of industry traction, lot of adopters. It's pretty stable at this point. There are still practical issues in running and maintaining a Hadoop cluster. There continues to be some challenges, but the technology is stable. A lot of people have adopted it. Amazon, Facebook, eBay. I know eBay. The numbers here are a bit off. It's not 500. It's about a few thousands, right? But yeah, a lot of guys. Elastic MapReduce is basically what we just spoke about. You have the map phase and reduce phase. What Amazon does is they are providing a service where you write the map and reduce jar and ship it to Amazon, and they will run it on their computers.
So Amazon will maintain our S3
Yes, so you will have to upload your data to Amazon first, and then when you need to run your job, you will hire some machines on the Amazon data center side and run your job there, and then that cluster will get shut down, and you will pay only for the time that your job ran. If we don't have access to a big cluster and we still want to use Hadoop, then you could do something like this, right? You pay them by the hour. You run a job for 1 hour, you just pay for it. But yes, the data has to be with Amazon.
It's time as it goes, as the name says, elastic.
Right. So when you start, they'll ask them, do you want 10 node or 100 node? You say 100, they'll spin up 100 for 1 hour. All right. So recap of what we just said. This is the data flow. You have the input data. All your input data feed into mappers. Mappers create intermediate key value pairs. Intermediate key value pairs then flow into. There is this shuffle phase where all your keys get aggregated, right? Like how your employee name and employee address became one array collection, right? So that happens. This shuffle phase is being done by the framework. We don't have to do anything here. Whether you like it or not, you're still going to get that. Yeah. And then you get data into your reducer, at which point you can run your aggregation logic. Yeah. Okay, so these are the 3 different pieces we need to write. First is the mapper, which takes in the key value. Second is the reducer, and third is the driver. Driver is the program that starts and tells Hadoop where all your input files are, where you can write your output, right? Basically, it gives the underlying framework some metadata so that it can start running your program. What is the location of the input files? What is the location of the output files? What is the name of my mapper class? What is the name of my reducer class? I don't know if this is too small for you guys to see, but in this example, what we are saying here is my mapper. I have a jar. Mapper is called foo mapper. My reducer is called foo reducer, and then this is what I am going to output. And then when Hadoop processes it and runs this, it runs the code. You don't have to look through this in detail because this is going to be generated by a framework for us, right? You will rarely write such Java pieces, right? If you have a very complex business logic that you have to implement in Hadoop, probably you might sit down and do this, but it would make sense for us to simply extend pig or hive and do it there, right? Or you could drop down to Scala or whatever. Good to know how it works under the covers. And the important piece there to understand is whatever code you write, it gets packaged and one copy of it is sent to all your nodes, which will then run it on the data that's there on the node. As long as we are clear about this, that's all we need to know. Yeah. Okay. So how do we start using Hadoop? So if you have access to a Hadoop cluster, nothing like that. If you don't, 2 ways to start. One way is really nice in the sense that Hadoop can run locally. You just download hadoop.jar. We could see that today, but we will probably run it on a VM. And then you can just java -jar hadoop.jar and give it your name of your class and it will run, right? Hadoop does not require that it be run on a cluster. They have a developer mode which will run just like any other jar, right? All the dependencies, all the different components, they have a mock setup which it'll work, it will just not be distributed, and that's more than enough for us to learn. It's even good enough for us to run simple programs. Just let's not run production code there. Yeah. Okay, another way to do it is companies that are working there, that are distributing Hadoop releases, for example Cloudera is one. They provide VMs, virtual machines. So if you have Oracle, VirtualBox, VMware, Fusion, you could download that VM image and run it. Yeah, and you will instantly get a one node Hadoop cluster that you could use. That is what we will be doing today. Alright, so the key to scalability is two things, one is MapReduce, another is HDFS. Alright, so we were talking about how HDFS stores data, right? Somebody asked a question, how is the data split? Okay, so this is what we already discussed. One file gets split into multiple copies and copied to different nodes. Yes, the advantages are obvious. Yeah, you immediately get reliable data store, redundancy, stuff like that. What are the disadvantages here? Duplication? Slow? True, slow is true. You probably have to create different copies, that creates overhead.
For real time.
Absolutely.
Okay, so normally Hadoop jobs don't run real time.
Hadoop jobs don't run real time, but there are other pieces to Hadoop which run real time. For example, there is a database called HBase that is a real time database, similar to how you would use Oracle. When we said slow, another point there, it might be slow when you are going to feed data in. There are other ways to work around it if you are willing to relax on reliability, but it's very fast when you read, right? Because you got 3 copies, and if 5 people request access to data, you can read them from 3 machines. If 2 jobs require access to the same data, right, you can run those 2 jobs concurrently because you have 3 copies of that file. Right. So it might be slow when you are storing it, but it's fast when you are going to use it. Right. And because the underlying assumption is that the machines are not server grade, right, you can use any cheap hardware. Typically we don't, but you could. Even if a machine goes down, you are still protected. Right. Okay. And another drawback here is you need this guy. There's this guy called the name node, right? What the name node does in this ecosystem of components that Hadoop provides is this guy you need somebody who will tell you, yeah, on node 1 you got piece 5 and 6 of this file, on node 2 you got the piece 7 of this file, right? Somebody has to maintain this metadata of where all these pieces are, and that is the name node. And one drawback is name node can become a single point of failure for you, right? If one guy is holding all the data about where all my blocks are and that guy goes down, I have no access to the data. It might be on the disk, but I don't know on which node in which point it's there, right? So it becomes a single point of failure. It also can become a bottleneck. If you have a lot of people trying to read files, everybody has to go ask the name node where that file is, right? And if name node is slow, then your entire system becomes slow. Right? The client first goes to name node and only then it can actually reach any node to read the real data. Make sense?
Is it possible to have multiple name nodes?
It is not. No. And so there have been developments there which bring in reliability to name nodes, but the practice in reality is it runs on really high spec hardware on one node, but the data, the real metadata is automatically backed up, so that if one goes down you can bring a copy up, right? You actually write to a secondary NAS mount and then you can bring it up from there. But this is one place where you don't want to go cheap on hardware, right? So it uses the same Oracle approach, right? How to do updates. You have your primary data store, and then you have your logs where you keep aggregating your changes. Alright, so Hadoop commands. So how do you read data from this data store? It's not a typical file system, right? There is this name node, there are the different machines that are storing the data. So how do you get data into it, out of it? The Hadoop jar itself comes with a set of commands, if you will, right? There is a Java API, all this is written in Java, right? So the Hadoop OS is Java, right? And the Hadoop jar that clients use to call the OS is in Java. Pieces of it in C++, but it's still Java. So if you are using the Hadoop client and you say Hadoop FS, what you're essentially saying is, I want to interact with the file system of my Hadoop, right? And then there is an XML which you have to give the jar, which will give you the address of the name node and stuff like that, metadata, configuration, right? So when you say Hadoop FS and you say ls, this is equal to running an ls in Linux. List the files in your file system, right? So this is how you go and access the file system. RM is again remove, you get put. Put is basically I have a file on my local desktop, copy it to Hadoop, right? Yeah. Are we clear about why you cannot do a plain ls on HDFS? If I am logged into, let's say I am working from Windows, yeah, and I want to view all the files that I uploaded to Hadoop, right? Why can't I do dir? Yep. Why can't I mount it as an external file system? If I have a network attached storage, right? All of us mount this network map network drive, or in Linux you can do a mount point, right? Why can't we do it here?
I'm not sure. Just same copies of the data.
Yeah, so you're right. So essentially this is being stored in Hadoop's own format, right? And they are managing how the data is stored. This is not a typical file system that the OS already understands, right? Some commercial companies have come up with the underlying file system driver which can expose this as a directory, but end of the day the entire architecture, entire format is being handled. It was created by Hadoop, right? Microsoft or the Unix guys didn't do it, so they don't understand this. You still have to call the Java jar. Java jar will call the Java API, which will get you the list of files, right? Essentially you are doing a remote call to the Hadoop server and getting the list, yeah, which is why you cannot do it there. You have to go through the Java piece. Alright, so I think we spoke about this earlier. There are a lot of support classes that are going to help us when we want to run a MapReduce program. We already know that the data is split in different nodes. We know that we need our Java jars to run multiple copies and read the data. So a lot of supporting classes that Hadoop already comes with. Input format is what we define, which essentially says my text input to my map face is going to be a text file, right? And then you have your map face, which is again a jar that we are going to create. This one, oh, I think it's too dark here, but this is map, right? This and this are the classes that we will provide. Everything else are classes that the infrastructure is going to give us. Yeah, they contain the logic to pull the data from different nodes, pull the data in an optimal manner, run different copies. All that logic is already built in. You just have to use those classes. Alright guys, I'm going to try to jump into this piece, right? Different parts of Hadoop. If I say I'm going to install Hadoop, what am I going to really install, right? This is what I'm going to install. Task tracker, job tracker, data node. Some of these things you will need to know. For example, the job tracker, when we run a job, you'll have to come here to see how your job is doing, how much percentage is completed. If it errors out, what is the error log, stuff like that. At those points, you will interact with these pieces, right? If you're going to run a job, then job tracker is something that you want to understand. If you're going to read data, then the name node is something you'll have to focus on, right? Yeah. The other pieces are you're having so many components because there are, it's similar to a client server, right? If you say a job tracker, that is the master, and then on each one of those 10 nodes you will have its counterpart, which will be your task tracker, right, which is talking to the job tracker. So it's always double. If you think of it, if you have to run a job, you have to store data, which means you have 2 tasks. In client server architecture, you can get 4 pieces. One is the server, another is the actual client which listens to that server's commands, yeah, which is why you have a lot of this stuff. When you talked about redundancy, the secondary name node comes into play. You could think about how we can do that there. This structure it still exists in some form, but the latest release of Hadoop has changed it. They are trying to move more towards a platform as a service, right? Essentially, when we said Hadoop is an operating system for a cluster, this really is the beginning of trying to provide a operating system for a cluster, right? So let me just maybe elaborate that for a second. All the programs that we are talking about till now, right, they are essentially batch jobs, right? You have a map phase, you have a reduce phase, end of it you have an output. So you start the program ends. But what is really an operating system providing you? It's providing you an ecosystem, it provides you an environment where you can run different kinds of programs, do different kinds of things, not just batch, yes? And that is where our yarn and the latest release of Hadoop, that is the direction that they are going to, right? But this underlying, the idea still remains the same, it's still backward compatible, but when you start moving into Hadoop 2, you might probably want to look into how this idea has evolved, right? But from a programmer standpoint, we are still going to do the same thing, nothing changes for us. Okay. So when you run your VM, right, I am guessing if you want to run a program and you really want to get your hands dirty on Hadoop, the recommendation is go download Cloudera's VM, right? It's called Cloudera Quick Start, 2 GB. If you want, I think I have a copy here. If there is a Wi-Fi, probably I can copy it for you guys, or you could just download it on your office network or wherever, 2 gigabytes. You will need a laptop that has 4 GB RAM, and when you open it in VirtualBox or VMware Fusion, right, this is what you are getting. When you start, you are starting a job tracker, you are starting a name node, and then you are starting all your task trackers, right? As soon as the VM starts, you will get these components running. You will be able to log into a browser and see the status of your cluster. Everything will be one copy. Obviously, you are running it on a laptop. But once you understand the big pieces, if I run a job, I need to go to the job tracker, right? If I am saving data, I am talking to my name node. Yeah, that's a big start, right? Once we clear that, from there on, it's all details, right? If you want to implement this particular application, this particular business logic, what do I need to do? Those are all more fine grained. Those things will keep changing, but the big pieces remain the same. Yeah, okay. All right, so when nodes fail, our jobs get re-executed. There is something called speculative execution. If say for example your cluster has been around for 2 years, right? Computers you added last year will be slower than computers you added this year, right? Which means any job that got scheduled on the old computers is going to be slow, and if the new computers finish their piece of work earlier, Hadoop will ask them to execute the old computers work as well, and whichever executes first, that will be your output, right? So it need not be just failure, it could just be to get your job to run faster. Your program which should have run only 10 times might run 12 or 15 times. All right, so let's jump into hands-on. Okay, so this is a screenshot from that video, right? So this guy posted a video of him playing with a saber, right? The Star Wars. He was trying to emulate that, and this video went viral. And we have access to an Apache server log during the time when it went viral. I think it was in 2006, and you can clearly see the impact that the viral video had on the site traffic, right? I don't think we'll be able to run the processing on the entire file right now. On my laptop it takes more than 15 minutes, but at least I have a reduced version of that file on which we'll run and see how we can generate some insights from that, right? All right. I'm sorry? 50? 1250?
Yeah.
Sure. Okay. Alright, so let me start my virtual machine. Is it visible? Yeah. Okay, so this is the server log. I'll open this log in a second once my VM starts. So what I have done is I have uploaded this file into my one node VM cluster, right? This one node VM that we just started. I've already uploaded it and it's present in a folder inside that virtual file system. Yeah, we have 3 copies of it. One is a small log which is just 2 KB, right? Another is 50K records which spans say 9 MB, which is really nothing. And then there is the actual log which is 1.5 GB. All this runs using the same code. If you had a bigger cluster, it will run in lower amount of time. The code doesn't change. Yeah. Okay, 4.6. This is the Cloudera distribution 4.6. I think it comes with PIC 12, Hadoop is .20, I think. Okay. Let's look at the log file.
What is the difference between, I mean, in Apache Hadoop website I can find only 2.3 or 2.4. You are saying some 4% from Cloudera.
Oh,
what
yeah.
is the difference between those both? I mean, I don't know.
There is no difference. So what they are doing is they are picking a version of Hadoop from the Apache website and they are packaging it, right? And they are selling the distribution to us or different companies with the with other guarantees like support, right? If you choose a Cloudera 4.5, 4.6, they will come with Apache Hadoop 0.20 or 0.21, whichever they choose. But if there is some problem, they will support it. That is the Cloudera version. So, okay, so this is the Apache log, typical Apache. You have your, is it too small for you guys? Better now? So we are interested in a couple of things. One is the date here, right? We want to pull the date. And let's pull the, I'm sorry? Let's also pull the person who referred this guy, this visit to us, right? So 2 pieces we want to pull. One is the date, another is the person who referred this particular visitor to our site. What we are trying to understand here from this log is 2 things. What was the number of hits that this website got on that particular day over a period of, I think, between 2003 and 2009. I think the data is, we have data for those 6 years. What was the visitor count per day, and which is the site that is contributing the most visitors to me? Who is sending me a lot of folks? I think Google will be pretty much in the top. A lot of folks are going to be coming from Google, but let's say you have a hyperlink on say YouTube and a lot of people are navigating to your site from YouTube. You want to understand that, right? You want to understand who is visiting your site and how they are getting to your site. Yeah. So those 2 analysis we'll probably try to run. This is my Hadoop code. I don't know if I should increase this a little bit more for you guys. Yeah, better. So what I am saying here is, number one, I want to create a map face which takes an input as text file, right, and load that into a particular variable. Basically I want to read a text file, I want to filter all the rows that have a get. I am interested in people who are retrieving HTTP pages from me, not people who are posting form data into me, right, and then I want to use this regular expression, right, to pull data. This is essentially what you will write in your map face. I got a key which is the byte offset from starting of the file, and then I have a line of data. Now I have to map that line to some meaningful data points, right. So here I am saying my meaningful data points I am going to extract, because this is unstructured, right. I am using a regular expression to pull something out of that line. The first regular expression is going to pull the date, right. Second regular expression is going to pull the referrer URL. If you look at the Apache format, you will see there is some structure to it, right. Date will be followed, preceded by a double quotes, open bracket, it will be the third field separated by a space. You can build some logic around it to pull these two fields, yeah, our usual regular expression parsing on text. So at the end of this, you have at the end of the map phase, we have pulled two things, one is the date, another is the referrer. To get the number of hits per day, you don't even need the referrer, right, just the date is enough. For each hit you get a row in the log, which means if you just count the number of date entries you have got, that is the number of hits on that date, yeah. So date does not require a referrer, we will anyways pull the referrer because it is easier for us to pull it in one shot rather than go through that file 2 times, yes, okay. So then how am I going to count the number of hits? We just spoke about it, you just group it by date and count the number of dates that are there, as simple as that, yeah, straightforward, right. Let us not worry about the syntax at this point, right. Syntax, there are different ways to write, at the end of the day generate this MapReduce jar, right. Pig is one, Scala is one, you could do a lot of things to generate the jar, but at the end of the day the concept does not change. All that I am doing is I am mapping some fields and then I am doing an aggregation operation. This should run inside a combine phase, it has to run, right. Every time you have a group you are going to have a combine, because only inside the combine you will have all the elements together, that is where you can count, yeah, makes sense, okay. So this is the count the number of hits by day, and this is where we are taking the same data set that we generated here, we are doing two operations, one is the group by date and second is we are grouping by referrer. Here we want to understand who contributed the most page views for me. So instead of grouping by date, let us group by referrer and then do a count, yeah, make sense, as simple as that. You group by referrer, then we do a count and then we do a limit top 5, which is our Oracle limit, just give me top 5, I do not want the long end, just give me the top 5 or 10 people that I am interested in. And then we are going to store this back into HDFS. This goes back to the batch nature of jobs. You do not have a UI, you cannot display this anywhere, whatever we generate, you have to dump it back to the file system and then view it from there, yeah, okay. I have a driver that is called run, which is essentially going to invoke this pig script. Alright, so we submitted the job, it created a jar file which would have given Hadoop two things. One is where my input data is, where it can create the output data. How does it know where my input data is? The very first line where we said load file name, right? That this is essentially read, parsed and a Java program is being created under the covers, yeah. So it knows where my file is, where it can write to and what are the steps. So it goes ahead and creates the file. I will show you what logic it has been using. It would have printed it somewhere above. I think I need to scroll down. So when you're seeing this query optimizer, that is where so I can read this out for you. I don't think you will be able to see this. The font is too small. But what it's saying is, inside this piece of logic that you just gave me, I directed two MapReduce jobs. It is calling it MapReduce 58 and 60, some ID, right? And then it goes ahead and does some optimization and figures out that I can do this probably in not less than 2 jobs. Sometimes it can combine it into one job, right? It can write a really big Java program which will do the same logic, except that the program will be very big. Here it chose to do it in 2 jobs. And let me zoom in. Okay, so by the time we saw that our programs ran, right? This is the output. I am using the 50,000 rows file, right? And this is the output of the first query that we ran, group by. Okay, so this is the output of the first query. On each of those dates, what was the number of hits that we got, right? This is in 2003, so if you look at the data for 2006, you would see a big spike there. 2003, all this were in the tens of thousands, right? But in 2006, this guy got like 1 million hits. He got 900 million hits in, I think, 12 or 18 months, right? So you would see a really big spike there. Okay, and these are the top referrers. Again, 2003. You still have MSN, search.msn, right? Search.yahoo contributing a lot of hits. I don't know if anybody goes to search.yahoo today. There is also vaxi.org, I think, and Ranchero. I don't know who these guys are, but these are the top contributors that we had inside that small file. Yeah. Okay, so I'll stop here. Take any questions that you guys might have.
Okay, if you guys want to ask a question, either use the microphone or repeat the question when, when they ask it, just repeat the question for the stream.
Okay. Yeah, I can repeat the question if you guys have any.
Okay, so you have the Hadoop system. Okay, now I want to know, like, can you do a simple database lookup over huge amounts of data with Hadoop efficiently? How will it compare to relational database?
Mm-hmm.
Let's say the querying time is within like 5-10 seconds and I have huge amount of data, and let's say I have huge amounts of system. Will it make sense to do a simple lookup through Hadoop or not?
Yeah.
Like
What you're asking, if I got this right, is you're asking, can I do a select name from employee where ID equal to 10?
Something,
Yeah?
yeah, exactly.
Okay.
Will it make sense to do?
So it depends. If you want to do this on a batch mode, if it's a batch program and you're going to do this for all the records, then Hadoop would make sense. But if it's for an online system where you need to do it in milliseconds, then you should start thinking about systems like HBase, which are built on top of Hadoop. They carry a lot of the advantages that Hadoop provides, but they also provide things like random access, doing updates, getting to a record very quickly, right? The NoSQL category of databases. But pure Hadoop MapReduce is intended for batch programs. You run a big job, you generate an output, and one of the use cases could be you load that output to HBase and ask the world to query HBase and not come to Hadoop.
Hadoop, okay.
So if you have a lot of data, do the processing in Hadoop, load it into HBase, right? Okay. If you really want to do this today in your office, I would recommend do it in Hadoop and then load it into your database, Oracle or MySQL, whatever you guys are doing. The adoption or the ease with which you could get into Hadoop will be much easier there. HBase carries its own learning curve and things that we need to be careful about.
Okay. Thank you.
Sure.
As far as I studied blog and some more stuffs, I learned that Hadoop is working good with HBase, as you said, and why not with Cassandra? I mean, Cassandra is also a scalable database and can store more documents there, and moreover, it works good with Mongo also.
Mhm.
And why not Hadoop goes well with Cassandra? Any idea or want to share?
Well, so I think it goes back to how these systems are architected. So what you're asking is, Hadoop works well with HBase but not Cassandra. Why?
Yes, yes.
So what Hadoop provides are a couple of things. It provides a way for people to store data into it, and it provides a way for us to run programs on top of the data, right? So it's up to the developers to write code in such a manner that they either leverage whatever feature Hadoop provides. Cassandra as a database, if you look at its legacy, it evolved on parallel lines. They do a lot of stuff that Hadoop already does, but they use their own storage mechanism, they use their own query language, right? There is no standard as far as NoSQL goes. Cassandra still does the same replication, right?
Yes, yes.
It does the same replication, but they have built it as a peer-to-peer system. HBase was built as a master-slave, right? So there are some fundamental architectural differences, but why can't Cassandra store data into HDFS? They could, but they didn't write it that way. That's basically the reason I would think why, right? The one thing that you could think of here is there are distributions that merge these two, right? But not in the way that you would expect. So for example, there is a company called DataStax, right? They provide a Cassandra distribution which has Hadoop, and that's different from Cassandra using Hadoop. So what they are saying is I can run Hadoop on Cassandra, but Cassandra cannot run on Hadoop, right? Cassandra doesn't have that code, but I could simulate something like a HDFS on Cassandra because Cassandra also internally does replication. Yeah.
Yes.
So from that is how they built it, right? And people are trying to converge right now because MapReduce is kind of like becoming a de facto standard. But can Cassandra write to HDFS? They didn't build it that way.
Fine.
So any more questions?
That's it. All right. Thanks, guys.
Thanks. And we have lunch outside. So